Hi, welcome to our pre-calculus. Topic today is sum and difference identities, problem type 1, radians. Last time we did similar problems in degrees, and the only difference for this lecture is that the angles that are given are in radians. Of course, a simple thing you can do is to convert your radians into degrees and then continue with whatever we were doing in the previous lecture. So that is one option. Option number two is just to get used to expression of angles in radians and continue with that. So remember that we have some basic sum and difference identities. Here I have listed them. Sine, cosine, and tangent of a plus b and a minus b. We said these all come from Pythagorean formulas, and we get to use them in the context of these problems. We had the reflection identities. If two angles are reflections of each other in x or y axis or the origin, then there's simple relationship between their sine, cosine, and tangent, and as the cases arise, I will explain that. We had a set of famous angles and cosine, sine, and tangent of all of them, and we are going to use these. So the idea is that if an angle is sum or difference of two of these angles, how can we obtain their trig values? And here are some examples we are going to look at today. For example, first one is find the exact value of cosine of pi over 12. So two approaches. One is pi itself is 180 degrees. 180 divided by 12, well, that's going to be 15 degrees. So that's same as cosine of 15 degrees. So then you can continue exactly what we did last time. So option number one is to say pi over 12 radians is same as 15 degrees. So cosine of pi over 12 is same as cosine of 15 degrees. And then, for example, how can you write 15? One option is cosine of 60 minus 45. And then apply the formula we had last time, which we are going to use again today. It's cosine of 60, cosine of 45, plus sine of 60, sine of 45. And then hopefully by now you have memorized this table, and you quickly write that cosine of 60 is 1/2. This is radical 2 over 2, and this is radical 3 over 2, and this is again radical 2 over 2. And then when you add them, denominator is 4 and numerator is radical 2 plus radical 6. So that would do it for this problem. Well, what if we want to become comfortable with with radians? So, and that's a recommended action here. So pi over 12. I want to write pi over 12 in terms of these angles. What is going to cause a bit of a problem for you is that the presence of this symbol pi here. So notice that pi is in all of these things. So we can pause for a moment and take 1 over 12. So we are putting pi aside, just take the fraction 1 over 12, and we want to write it in terms of fractions that we have. Well, what fractions do we have? We have 1/6, 1/4, 1/3, 1/2. These are the fractions that we have. So the idea is to take a fraction 1 over 12 and write it in terms of two other fractions. Well, obviously 1 over 12 is smaller than all of those fractions. We cannot write it as a sum of them, but perhaps we can try to write it in terms of difference of them. So if 12 is coming out of a common denominator of two fractions, what could be their denominators? Well, you have a set of choices, and you do a little bit of trial and error, and you notice that 3 and 4 is going to work for us. Now, how can I make two fractions such that their sum or difference becomes 1 over 12? We said, well, adding them is not going to work because, well, either of these fractions is going to be bigger than 1 over 12. So more than likely I have to subtract. Well, let's try the simplest one, 1/3 minus 1/4. If you take common denominator, you see 4 minus 3 over 12. That's going to work. You take all of that, multiply it by pi, so it becomes pi over 3 minus pi over 4. So the most difficult part of the problem is dealing with fractions. So if we saw pi over 12, so well, let's think about just 1 over 12. Let's take 1 over 12 and write it as difference of two fractions, 1/3 minus 1/4. You obtain this thing by trial and error. Then go back and complete this one. And then you can say cosine of pi over 12 is same as cosine of pi third minus pi fourth. Now you apply the cosine formula. Here's a cosine formula for difference. So cosine plus sine. So that's easy to remember. So it's going to be cosine of pi third cosine of pi fourth, and then we have plus sine of pi third sine of pi fourth. This is exactly what we did here, just that we did it in degrees. Pi third 1/2 pi fourth radical 2 over 2, sine of pi third radical 3 over 2, sine of pi fourth, again radical 2 over 2, and we get the same answer that we got above. It's just radical 2 plus radical 6 over 4. Well, given that the work we have done above, we can do this thing quickly. This is sine of pi over 12. Up there we learned that pi over 12 is pi third minus pi fourth. So we take advantage of the work we have done. Sine of difference is, well, here's the sine of difference. Sine of A cosine of B, cosine of A sine B. Try to memorize. The way you do it is that when you come across this, write down what you think it is, then go back and check. If you are incorrect, rewrite all these 6 formulas one more time on piece of paper. Okay, so we said writing and reading and talking, and these analog activities are going to help you learn the mathematics of it. Write all of 6 formulas, repeat it to yourself, say it loud, repeat and repeat until it all falls in place. So sine of first, cosine of the second, minus cosine of first, sine of the second, and we just fill in the details. Sine of this is pi third or 60 degrees. Again, what you want to do is it's going to be a extensive exercise to rewrite this table over and over again until it falls in place for you. So this becomes radical 3 over 2 and radical 2 over 2, and this is 1/2, and the other one is again radical 2 over 2. Okay, so these things we have to know from. What I recommend that you do is to memorize these 3 triangles. That's a lot easier than memorizing that table. So 30, 60, and this is going to be 2, 1, radical 3. And then you need also same thing for 45. So for 45, It's 1 and 1 and radical 2. Perhaps that is sufficient. And of course we had one for 90 degrees, but we rarely use that. So here's a denominator 4, and radical 6 minus radical 2 will do this job for us. That's the final answer. 11 pi over 12. So I want to take 11 pi over 12. So option number 1 is convert this thing to degrees. You say, here's a convenient thing. This in radians is same as 15 degrees. So then, 11 pi over 12 is going to be 11 of these is going to be 165 degrees. Okay, in the 165, for example, you write it as 120 plus 45 or other options. How about in radians? You said take 11, 12, break it down. How do I break it down? Denominators 3 and 4. Let's try addition. How can I make two numbers here such that when I add them I get 11? Well, 2 times 4 is 8 and 1 times 3 is 3, and that's going to do it for me. 2 and 1, because this is 8 and 3 adds up to 11. So I did a bit of trial and error there, and then I get that fraction just multiplied by pi, then you are all done. So if I want to do sine of 11 pi over 12, it's going to be sine of 2 pi third plus pi 4. Then I remember the sine formula: sine of first, cosine of second, plus cosine of first, sine of the second. And now I replace, this is 2 pi third, sine of that, radical 3 over 2, radical 2 over 2, cosine of 2 pi third, that's going to be minus, what's that, minus 1/2, and this is radical 2 over 2, and then we get radical 6 minus radical 2 over 4. Okay, so cosine of 2 pi third, either you come to this table, cosine of 2 pi third, or you can use reflection identities. Let's just go ahead, apply that reflection identity for answering this case. Where were we? Cosine of, so here, cosine of 2 pi third. So this is like quick geometry to help us to get our bearing. 2 pi third is where 2 pi third is going to be in the second quadrant. So this is 2 pi third. I want to know the cosine of this. Okay, since I know I'm more comfortable with the first quadrant, it would be nice to have to deal with just half of this table in the first quadrant and not to bother with this larger angles and these negatives here. So how do we reduce the job for us? So cosine of 2 pi third, let's apply the reflection identities. I go for cosine, take a reflection in the y-axis. When I come to this side, well, this angle now is going to be pi third. Cosine of this, and the original one, that we draw it in a different color, cosine of 2 pi third, I come down here, and this is the cosine of 2 pi third. Cosine of pi third, I come down here, and this is cosine of that one. So cosine of 2 pi third is negative of cosine of pi third. Okay, by reflection identities, these two cosines, one is positive, one is negative. Now cosine of pi third, hopefully I remember in the first quadrant what the story is. Cosine of pi third, I remember it as a half, and this becomes therefore minus a half. So this was a roundabout way of deriving for ourselves what the cosine of 2 pi third is. If we don't remember the values of cosine in other quadrants, we just remember in the first quadrant, that's enough. If we can apply the reflection identities, we can get the similar answer instead of trying to memorize. Okay, let's try one more thing. Tangent of 7 pi minus 7 pi 12. First of all, how about reducing our job by getting rid of this negative? So I say tangent of minus 7 pi 12 is actually same as minus tangent of 7 pi 12. This one you might remember from odd even identities. Odd even identities told us tangent of minus theta is minus tangent of theta. Odd even identities fall in the more general category of reflection identities. So if I have an angle, theta, and I have another angle minus theta, these are reflections of each other in the x-axis, and that falls under the category of reflection identities for tangent. If you have two angles that are reflections of each other in x-axis, then one of them is going to have a positive tangent, the other one is going to have negative tangent. And we have many other possibilities also in the reflection case. Here we're just looking at reflection in the x-axis. And that's what odd even identities are. Okay, next step, we have to take 7 pi 12 and break it apart. It's easier to put the pi aside and ask ourselves, well, can you take 7/12 and break it apart? Let's do a trial and error. Do I want to do subtraction? Do I want to do addition? Let's try addition first. What are the denominators? Well, try 3 and 4 first. Let's see if it works. How can I make 7? Well, it's rather obvious. One of this and one of that would do, because now 4 and 3 makes you 7, and then you're all set. So this is really pi third plus pi fourth. Now let's make sure we don't lose our track. What we want is negative of the tangent of this. Now I'll go ahead, calculate the tangent, and not to forget, at the end we have to kick it with a negative to get our final answer. So we say tangent of, well, what was our formula for tangent of the sum? So 7 pi 12, tangent of the sum of the tangents over 1 minus product of the tangents. So here, sum formula here. Tangent of the sum is sum of the tangents over 1 minus product of the tangents. So that is what we are going to do. So it's going to be one big fraction. Tangent of the ingredients pi third and pi fourth have to be added, and then 1 minus the product of exact same two items we had in the numerator. Now again, tangent of pi third, several options. Do you remember it from the table? Okay, so that's a table lookup, but we said it's smarter to derive these things so that it becomes second nature. Looking things up is not Well, it's one level of understanding things, but higher level, let's remember the picture. Let me write in degrees, or you can write in radians. So this is of course pi 6 and pi third. What were the form numbers? 2, 1, radical 3. Is that right? Now tangent of 60 degrees is going to be ratio of 60, ratio of opposite of it divided by adjacent of it. So it's just obviously radical 3. Okay, so we went through a little bit of reasoning, but that helps you quite a bit compared to uh, looking up at the table. Okay, looking up at the table is fine, but it's a bit low level. If you want to help yourself long term, draw a picture. Okay, uh, radical 3, tangent of power 4. How about power 4? Let's do that. Pi 4 is this isosceles triangle, 45 degrees. So 1, 1, radical 2. Tangent is ratio of opposite to adjacent. It's just obviously 1. 1 minus radical 3 times 1, which is obviously just what we have in the numerator. Radical 3 plus 1 over 1 minus radical 3. Now, that is good enough, but we can go a step further. So if you want to stop here, that's fine. But again, I insist that you practice your college algebra. Make sure that you rationalize this thing to clean it up. So rationalize radical 3 plus 1 over 1 minus radical 3. We multiply by, what did we say we do? Multiply by conjugate of the denominator. What's a conjugate of the denominator? You just flip the sign. That's all you do. Happens to be accidentally whatever we had over there, but that is, again, just accident. What is great about conjugates is that when you multiply them, the cross term cancels, and all you get is difference of the two squares. So it becomes 1 squared, which is 1, radical 3 squared, which is just radical 3. Numerator, you multiply, we have radical 3 times 1, another 1 times radical 3, that is 2 radical 3's. 1 times 1, radical 3 times radical 3. So numerator became 1 and 3, I add them, 4, 2 radical 3. Denominator is minus 2. To avoid a certain common mistake, which is to divide just these two, you are advised to factor first 2 plus radical 3, and then divide. These two cancel, a minus is still there, so it becomes minus 2 plus radical 3. We had to borrow space from the next problem. Now it's possible that we've kind of got lost in the track of things. We started from tangent of 7 pi 4, 7 pi 12, and this is what that one is. But the original question was tangent of minus 7 pi 12, which is minus tangent of 7 pi 12, which is minus of this, and that makes the minus evaporate. So I'll have final answer, tangent of minus 7 pi 12, minus minus becomes plus. The cleaned up form is this. If you wanted to stop here, remember you still have to multiply by a negative to be done. So this problem we needed extra space. Did not anticipate. Okay, 5 pi 12. So what is 5 pi 12? We learned our process. We take 5 over 12. So can I write it as the sum? 3 and 4. Well, smallest I can make with these things is going to be 7. Is that right? If I have 1 times 4 plus 1 times 3, that makes 7. I'm already above the 5 that I want. So what do I do then? So we said, well, this process doesn't seem to be successful. So let's try plan B. 5, 12. Let's say suppose I want to subtract these fractions. So which one is first, which one is second? You do trial and error until something works. So 4 and 3. How can I make, now this time we are trying subtraction. So how can I make some multiple of 3 minus some multiple of 4 to become 5? Again, it's a problem in a branch of mathematics called number theory. Something there helps us answer this kind of questions. But here, your best bet is just to use trial and error. So after a few trials and errors, you see that 3 and 1 works here because 3 times 3 is 9, 1 times 4 is 4, 9 minus 4 is just 5, and that one would do it. So I'll have then cosine of 5 pi 12 being cosine of 3 pi 4th. Okay, so cosine of pi 3rd, and for subtraction we'll have sine of 3 pi 4th, sine of pi 3rd. Now, sine and cosine of 3 pi 4th are like multiples of radical 2 over 2. For cosine is negative, so again you can either use reflection identities or use this table. Cosine of 3 pi 4th minus radical 2 over 2. Sine of it is going to be radical 2 over 2. If you want to avoid using the table, avoid using the table, then we have to use the reflection identities. They are going to, or odd even identities, they will do the job for us. So minus radical 2 over 2 for the first one. Cosine of pi 3rd is just 1/2. Sine of pi 3 pi over 2 is radical 2 over 2, and sine of pi 3rd is radical 3 over 2. And we come back to our familiar expression. I write the positive first, radical 6. It's convention to write that first, and then radical 2 over 4. So how do we use reflection identities? For example, in this problem, again, we have 3 pi over 4. 3 pi over 4 is an angle in the second quadrant. It's 3 pi over 4. I'll do a reflection in the y-axis. So we get this comfortable angle. This is pi over 4. By comparing the coordinates, we can see that cosine of 3 pi over 4, cosine of 3 pi over 4 is on the left. Cosine of 3 pi over 4 is this. Cosine of pi over 4 is this one. So they are off by minus. So this is minus cosine of pi over 4. And pi over 4 being first quadrant, we know what that is. Radical 2 over 2. So from that conversation, we arrive at this minus radical 2 over 2. So again, I want to emphasize that doing that type of reasoning is going to help you quite a bit. How about the sine? Well, with respect to sine of these two angles are the same. This is the sine column. Sine of 3 pi over 4 and pi over 4 are the same thing. They're both radical 2 over 2. They're both radical 2 over 2. And that's what we used here. Here and here. Excuse me. Sine of 3 pi over 4 is just radical 2 over 2. And that's what we used. Okay. So that was for that problem. Final answer. 13 pi 12. What's the story with that one? 13 12. Well, let's try. Let's see if we can break it up to fractions with denominators 3 and 4. So what can we do, for example, here? What do you suggest? What numbers here and here will do the job for us? I want to make 13. Well, what times? So what we are asking, the question is the following. Take 13, write it as some number times 4 plus some other number times 3. What works? Well, obviously 1 of 4 and 3 on 3 will do the job for us. And so I have, and we multiply by pi, of course. And therefore, we have cosine of 13 pi over 12 is cosine of pi over 3 plus cosine of, oh, excuse me, um, 3 pi over 4, and that's cosine of the first, cosine of second, minus sine of first, sine of second, and 1/2 minus radical 2 over 2 minus radical 3 over 2 times radical 2 over 2. The whole thing boils down to minus radical 2 and minus radical 6 over 4. Okay, so we practice these 6 formulas. Now, remember, we still have to show where do these formulas themselves come from, and that's a one higher level than what we are doing here. What is the original reasoning behind the formulas? So if you want to go in any area that would take you deeper into mathematics, you need to push yourself to do that. What is the reasoning behind the formula itself? So all sorts of theoretical engineering or mathematics, analytics, and so on will require that kind of practice. Okay, hopefully that's going to be done sometime in the future and as an additional lecture. Right now we are just practicing how to use the formulas themselves. Until next time, good luck and God bless.